but it was burning away when I left. So I'll get all the lectures up there for the ones that need the lectures, and I'll also get the homework assignment once our remote student, who has been getting nothing for the last 2 weeks, gets those. Make it all fair that way. And I may shorten the homework assignments too, so just get an idea.
Is it posted?
Huh?
Is it posted?
No.
Okay.
No. I may shorten it because I'm giving you guys compressed time on it, so it's gonna, maybe I'll give you, if I'm gonna give you half the time, I'll give you half the work. Something like that. All right. So far, as we've been working up the class, right, we've been dealing with old to new to understand how we got there and understand all the networking decisions that were made to get there. I think it's better to do it that way because if we just started with even where we were at on Wednesday, if we just started with that, right, and we started talking backwards in time about contention on why is there contention on Wi-Fi versus no contention on LAN, right? It would just be confusing. So I structured the course that we come from the bottom and working our way to the top. And we've almost got to modern networking. So for the most part, some of the stuff that we've talked about with switch data link networks is modern, right? That is current technology. That's how it actually works. We talked about IPv4, which is modern-ish. If you check, I'm not even looking, I haven't looked at UCCS, but if you check your Wi-Fi, if you're connected to the network, you might have an IPv6 address. Most modern, even home routers now forward on IPv6 addresses. And so let's talk a little bit about IPv6 today. So you're looking?
No, I don't like IPv6. But yeah, I do have an IPv6 address.
Okay. So let's talk a little bit about IPv6. And you'll find out that from looking downwards into the backwards landscape of IPv4, there's not really not a lot of difference, right? The addresses are longer, which allows for many more addresses than what we currently have in IPv4. But looking backwards in the technology, there's not that much of a difference. As we go forward to quality of service, there are things that were added to IPv6 that actually help, mostly with being able to directly label a flow inside IP header so that we can possibly, not guaranteed, but possibly deliver them in the same route, much like you would do in a virtual circuit. So we'll take, and as we get to TCP, you'll see that we use flows a lot in TCP because you want them, but then the routers need to actually keep track of the flows themselves, and where IPv6, the header can actually have the flow labeled inside it. So.
I do have an IPv6 address, but it says link local. So it may not actually be a true routable one.
Okay. And that's still often the case. So you can have an IPv6 address and still be netted. Which isn't always a bad thing from a security perspective. The way people aren't reaching out and touching you directly. So, what is the main motivation between IPv6 and IPv4? We ran out of addresses, right? So we have 32-bit addresses in IPv6 or IPv4. So in version 4, we have 32-bit addresses, which is about 4 billion addresses. Of course, it's not really 4 billion because you have, whole segments that are non-routable. You have multicast. You have special reserve addresses at 0 and 255 or broadcast and blah 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 blah, right? So it's not really 4 billion. And it turns out, well, we got about 10 billion computers connected to the internet right now. And if we had 10 billion computers connected to the internet, how do we use 4 billion addresses? Well, the answer was nah, right? It's a non-optimal solution, right? We might have talked about this really early in the network, that in the theory of networking and information sharing, it is a fully meshed network, a fully interconnected, that is the most useful. And it is exponentially useful. So a network of 10 versus a network of 100 isn't 10 times more information. It is actually exponential. And while it might not be 100 times more useful, right, it is bigger than the sum of its parts. And so IPv6 allows us to have public addresses for a lot of computers. How many computers?
2 to the 128th.
2 to the 128th computers. Again, with the caveats that whole swaths are taken out for the military and blah, blah, blah. But still, it's a lot. So our address space becomes 4 times as big. We go to 128-bit addresses, but that is not 4 times as many addresses, right? That is 2 to the 96 times more addresses, right? It is an extremely large number. Right? We're talking about the grains of sand on Earth kind of large numbers, right? Big, 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 big number. So the main benefit of IPv6 is these large addresses. And the reason we're doing that is because, and I believe this is true now, I believe so there's IANA, the Internet,
Signed names and numbers.
yeah, Signed Names and Numbers Authority, right? They had the original like blocks of addresses that was divvied out to regional routing authorities, ARIN being ours, and then there's AFNIC and RIPE and AFRINIC and LATNIC. And so they were divvied out addresses so that they can assign those. I'm pretty sure now all of those routing, with maybe the exception of AFRINIC, or AFRINIC, it's AFRINIC, has divvied out all those addresses. There are no more addresses to be divvied out. Of course, companies got addresses, and now there's a secondary market where people are selling them for more than they got them for to begin with, right? But they're all empty. So that means that when you acquire an IP address, when you turn on your home router at home, or you get a static IP address because you're running a business and you have public IP addresses for your web server or whatever, that means that somebody else had to give up an IP address to get that, right? They are all gone. And so now there's this crazy IP address sharing game that's going on. If you're running completely on IPv4. Of course, that doesn't mean that you can't have IPv4 at home and then NAT it to an IPv6 or vice versa, right? And we'll talk about actually how to do tunneling and how that actually works. So let's take a look at the IP version 6 addressing scheme. So IPv4 was 0 to 255 in dotted quad notation, right? Of course, in reality, right, that could actually be written like this. In hex, right? So no big leaps of faith yet. So now let's come up with a 128-bit address. What would that look like? Well, we're going to do them in sets of hex decimals. I don't know if it's 0, 0, because it could be any number, but 128 bits. Right? So this is what our new address looks like. Awful. Right? And so this could be zeros to F's all the way across. Of course, real things would not quite look like that, so let's put some more reasonable numbers in here that look more real. Okay, so this is more like a real address. Of course, you never want to write out all of that, right? So there are shorthand notations for it. The rules being that if you have a long string of zeros, like the entire quad or the entire quads or double quads are all zeros, you can just omit them and show that you've omitted them with a double colon. All right, so then we can do this. And just kill that one, and that one. And by the way, some of these F's are actually broadcast, so we wouldn't actually do that. But, and then we can actually also omit any leading zeros. Because 00FF and FF are the same number. Just like if you had decimal notation with leading zeros, then that, 00100 is 100 no matter what, right? So you can just omit those. But that's as good as it gets. But the IP addressing scheme isn't awful, other than it being really, really large numbers. And just like before, you may have private numbers. I believe 2601 is a private number. At least it shows up on my Apple router. Should look at that. But the big advantage is that now we have ridiculous large numbers. Also, we won't discuss why, but it also has some other properties. So we haven't really talked about, everything we talked about so far has been unicast, one computer talking to another computer. We haven't talked about, and we talked about broadcast in the sense of having to find routes and unknown paths through data link, right? We haven't talked about multicast, which is one computer talking to many with one packet. Because it's easy for one computer to talk to many with many packets. It's less easy to do it with one packet. And then there's also a more strange topic called anycast, where it's one packet sent to the nearest computer and the nearest computer only that is in the group. So multicast, you have a group, one computer sends to that group. Anycast, you have a group and one computer sends to the nearest member of that group. And you might be able to think of some neat things that you would use that for, right? For maybe it's for content delivery, right? Maybe it's for sensor data, right? If you have an alarm, maybe it's only one of the control circuits that need to be alarmed, and then the alarm takes it off, right? So while IPv6 is also a newer standard, it is also less complicated than IPv4. So if you remember in version 4, we had all sorts of flags and we had offsets and blah, 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 to figure that out. Yeah, we just get rid of all that. It turns out that we didn't, even though we built fragmentation into IPv4, it was actually less useful than doing sourcing, right? So we ripped that out. And so our header just is version, differentiated services again, both of those were in IPv4, flow label, which was not in IPv4, and then length, next header, and hop limit. And source and destination.
It says 2601 is hosted by Comcast.
Oh, 2601 is actually Comcast?
Yeah.
So that's interesting. That means that Comcast is actually passing you publicly routable IP addresses to your home computer, which means that we might be able to tag. Maybe when we get into security, we'll see if we can tag somebody's computer local.
Cool.
I didn't think it would be publicly routable. That's why I took a guess.
So how long is the header then?
So each of these is, again, set up like last time. It was 32, 32, and then of course 128, 128. So it's extensible. We have next header. So we can actually add header information into that. But next header most often points to the packet labels. So like actual data. So next header would be the TCP header that is, or UDP or whatever that's buried underneath it. But it is extensible where you can actually add information. So if you guys have ever done any looking at like the MFT records for Windows file systems, right? It's a linked list, and basically that every entry has a next entry, right? So that it can be as big as you want. Version is obviously just 6. Differentiated services hasn't changed. The only thing that's really changed here, other than stripping out all of our flags and all of our offsets and all of that, is we have the flow label. Flow label can now be used by routers, and this is built into the standard, right? So if a router is supporting is version 6, then this can be used and will be used by routers, and that is basically a randomized number set by the communicating computer to just give the flow, whether it be connection oriented or connectionless, the same route through the internet, or even if it's just one computer or local computers, right? It gets the same route. Why is that important? We haven't talked about the transport layer yet, because the transport layer actually does this. TCP already does this. But why is this important? So it could be useful for throttling, and it's definitely adjacently useful because of throttling. So if you are sending out datagram packets and they're choosing random paths through the internet, and we're going to start talking about routing today, and we'll hint about how routes might change because of hotspots, and we'll get to that later as well. But let's say, for whatever reason, you send out a stream of 100,000 UDP packets, i.e. it is VoIP or video conferencing, both of which go over UDP, and they take different routes at the internet. What happens at the end? What is likely to happen at the end if they took different routes? They're going to be out of order. If they take the same route, can they be out of order?
Potentially.
How?
The router would have to buffer it and then select a different router.
Correct. So when we get to actually doing queuing and quality of service, right? If it's not a first in, first out queue, right? There may be some algorithm that chooses one over the other, right? But very likely, if they take the same path through the internet, while some may be missing because this is a connectionless service, right? They shouldn't be out of order, at least not often, right? So things might just be missing, but should be in order. Right? If you can have this semi-guaranteed order, then you can have like half connection oriented, quality of service, right? So if you're missing a bunch of packets, you can, and they're all in order, and they're not just taking a different path through the internet, then you might notify, as the receiver, you might notify the sender, hey, you need to throttle back, right? Send smaller packets, right? Or send them less often. And when we get into transport, you'll see why we have to do that. Because it turns out that the way we throttle things is to send it as fast as we can until we just lose them. And then we throttle back a little bit. And we continue to do that over and over and over again. So packet loss is a normal thing inside of the network because we're all trying to use bandwidth. Right? So now we just, instead of having TCP manage all this or having homegrown UDP systems that are doing this at the application layer, let's just build it into the network layer because it is in fact a network function. And so we build that in.
So does that mean the router has to memorize all those flow labels then?
Sure, but only for a little bit.
Okay.
So the nice thing is every packet coming in has a flow level, right? So you don't have to say, oh, we're gonna keep this for a minute or whatever, right? It could be actually a very short time. It just auto renews itself every time it comes through because it has to look at the flow level anyway, right? So you might have it set at 1 second, right? And so if that's a reasonable number, then you might have it set at 1 second. It just keeps renewing itself every 10 milliseconds or so. And then when 1 second elapses, you can just assume the flow is dead. So it's not like, so if you didn't do it that way, you have all sorts of other issues, right? Because what happens if you have 20,000 flows and that are started in a core router every minute, then they're going off and on and off and on, and right, and you have to extend it out for a minute because, or like a video conference is an hour long, right? So if you have hour-long video conferences, now you have to keep 20,000 flows that are started every minute for an hour. That's really large tables, right? But if you just auto renew every time it comes in, then you can have basically just a sliding window as you go down. And now instead of doing 20,000 times 60, you're only doing 20,000, basically. So we have IPv6. What is the problem? Why can't we just switch over entirely to IPv6 today?
Hardware.
Hardware. Right? There's some really old things running on the internet. Some of them are important. Really important. Right? IP version 4 and version 6 are inherently incompatible. So this becomes a internetworking problem at the network layer. So the network layer was meant to solve internetworking problems, right? We had different data link networks, local networks, and they all, they had different standards, different packet sizes, different addressing, blah, 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 and the network layer solved that. So now we have a internetworking problem at the network layer. How do we solve that? With some ideas. Tunneling. And we are going to go into that because that one's the most useful and will be useful for other information, particularly VPNs later. So we'll go into tunneling. What else? You have it on your computer right now, right? You have both an IPv4 and an IPv6 address, right? So you could just, that's called dual stack. We're just going to run both, right? Maybe try IPv6, and if it doesn't work, fall back to IPv4. What else could we do? We could have routers translate, which is an awful idea for a number of reasons, right? But we could have routers translate. So that's an awful idea because IPv4 has to support fragmentation, right? And so IPv6 has no inkling about fragmentation, right? So now is IPv4 or 6 in that sense is lossy, right? So if you're going to translate from 6 to 4, what do you do to fill that information in, right? And now you're also loading the routers to do that. The routers would have to do all that computation. So there's a bunch of implementation ideas that we could come up with, right? To run dual stack, which you're actually doing now, or we could do tunneling. And we could have the routers do the work. We could maybe have the routers do the work, and unless something else happens, right? Maybe we can negotiate between hosts, right? Maybe we could do pathfinding between the network so that we never run through. If we're going to use 6, we don't run through a 4 network, right? Try to do pathfinding. There's all sorts of things we could do, right? So, but I do want to talk about tunneling because tunneling is going to be very useful to us later. So, let's say we have, and this works both ways actually, kind of. Let's say we have network A over here and network B. This is a 6 network, and a 4 network. And we want A to communicate with B. These are networks, by the way. But it's a computer on network A to talk to a computer on network B. The problem is they're only connected with via IPv4 network. How do we do that?
Encapsulation?
We're going to encapsulate it. So remember, we've been drawing these diagrams. So right here, this device, and it has to sit on both IPv6 network and IPv4 network. This isn't all that much different than this sitting on a Ethernet data link network and a point-to-point MTLS network, right? It's not really all that different. So if a packet arrives here, right, it has the network layer, and the data link layer and the physical, right? And then we go up the stack and we translate. If it was last time, we would translate like, okay, the network just gets copied over, kinda. Right, and then we put the new data link network. So let's say this was data link Ethernet, and then we say data link MTLS, right, in the physical, right? We just translate over, copy kinda the network over, and then do data link down, right? And then it's only we do the kinda on network because sometimes we're going to fragment packets, blah 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 blah, right? So we don't actually have to do much different than that. So this time, let's just say, hey, this is network version 6, right? So what are we going to do? Well, we're just going to climb up the stack again, right? And we're going to say, oh, this is a version 4 network, so let's just put a new header on this called network version 4, and then what do we put inside it? Well, it's all of this stuff, right? So net 6. Data link, this might be Ethernet now, it doesn't matter. Right? And so it's actually the same thing. The only weird thing we're going to do about it is we're going to have 2 network layers. But remember, IP, with one very rare exception, or actually not even that. So IP is totally unaware of what is inside its data packet. Right, with the exception of the point to whether it's going to be a UDP packet or a TCP packet. There is in IPv4, there is a protocol field, which we can predict off over there. And I believe that's still in differentiated service in IP6. So all we do is just encapsulate it. And the only thing we really do that's any different than what we've done before is we simply put 2 network headers on. Essentially, this looks a whole lot like a virtual circuit, just like MTLS. Remember, MTLS put a point-to-point protocol header and then the MTLS data link layer on it, right? And it transported from one router to the other and then ripped them off and sent it on the network again. So we are asking the routers to do a little bit of work here, put a IPv4 header on it and send it to the other side and rip it off, just like MTLS. The only thing different now, instead of ripping the data link layer off, like we did before, we're just ripping the network layer off. And inside is, voila, another network layer. Now, point A can have an IPv6 address, B can have a version 6 address, and they can communicate to each other, so long as these know what they're doing. And it works a lot like MTLS would work, right? These still have to be pre-configured, right? Because they have to know that this network segment over here is on the other side, right? But we can do that. We could also do that with, you could come up with the same setup with 4 addresses on each side and a 6 in the middle. Right? There's no difference. We can just encapsulate that stuff. Now we'd have to do some pre-configuring to make sure that all the routes have the right size, whatever, and this route rejects packets with ICMP and stuff, right? So we'd have to do some work overhead to do it the other way around to do pathfinding, right? But it would still work. And this should give you a really good idea on how VPNs work. Right? So you basically have a local packet that's sent to the router, and if your router is doing the VPN work for you, you have a nicer router, not super expensive, but you have a nicer router, then it will do the VPN work for you, and it will encapsulate that and send it to your VPN server, which rips off the encapsulation. Also notice that there's nowhere did I say there was encryption for this, right? So VPNs, at least in older versions of VPN, was it led you to believe that it was actually a virtual private network, where things were actually private. It doesn't have to be. Newer VPNs also encrypt the data packet as they send it over, but VPNs are basically take the same idea. Most VPNs actually function on your host, right? Your host itself does the encapsulation and just routes it to the VPN server. So, we have talked about forwarding, whether that is forwarding version 4 or version 6 packet. We haven't actually talked about routing. So there's a difference between forwarding and routing. Forwarding is simply looking up at a table which way to go, where to move forward. Routing is actually discovering the path that actually exists to make that happen. So far we've been magically looking up tables, right? So in this network, right, it's not A talking to B, right, through this isolated linked network, right? Each of these nodes have many, many networks attached to them. So in order to actually forward those packets correctly, you actually need to discover how to do the route. So let's talk about just how to discover the route. So we've already done one really, really simple routing protocol called spanning tree. right? If you remember back to the data link network, we did spanning tree, which found a route through the network. And I think the path, it looked like this, right? We had like a bunch of computers. Right, and they were interconnected. Right, and we come up with a spanning tree which basically turned off ports so that we wouldn't have, because of the way that data link layers work, and they're basically use broadcast at every port. So every receiving port actually duplicates the packet and sends it out to multiple ports, and we got cyclones, right? We got packet storms inside the network if we had loops, right? So we came up with an algorithm to actually remove loops so that there was only one path through the network. We just turned ports off. Right? We turn ports off so that by looking at the lowest Ethernet address and deciding who's in charge and blah, 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 and we find one path through the network. The problem with this is that it might be very useful to have multiple paths through the network. So spanning tree can actually handle when a path dies and then just turn on the port. So if this path dies, right, then it would know to turn on this port. Spanning tree can actually handle that. But that's not necessarily what we're asking here. We're not looking for things that are dying. We're looking for other things. Like we would like to have packets to go both directions out of that. It would be very useful to go both directions, particularly in an internetworking concept, because now we can utilize the network, right? We have multiple bandwidth paths, and if we use spanning tree, not even saying it's possible because you'd actually have to have a route to every single port in all the internet, right? But the whole concept of spanning tree, that means that if you go to Google and I go to Netflix and somebody goes to Hulu and CNN, blah, 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 somewhere in the core of the internet, we're going to share the same link. We have to, because there can't be multiple links, right? So that means even if we're in different parts of the country, some middle part of the internet is going to get overwhelmed. And we would like to be able to have multiple paths through that in an interconnected network to at least share bandwidth. Or share something. It turns out it might not be bandwidth, right? But we would like to have multiple paths exist. So we would like to find out a way for that to actually happen. So we need to find an algorithm that is, again, fully distributed and always correct, right? So we're in the same predicament we were with spanning tree in data link network. So we need to have it as fully distributed. We can't have somebody in charge, right? We might be able to elect, in spanning tree we elected somebody in charge, sort of. But so something that's fully distributed and always correct. But we would also like the algorithm probably to find efficient and fair paths through the network. That is less important than correct, but we would like for it to find those things. And we'd also like it to scale to internet. And I'm going to throw this one out there. We would also like it to converge quickly. So we're going to go through a couple algorithms right off the bat that will solve all of these things other than convergence. And convergence means if something changes in the network, in particular if something dies, how long does it take to fix that? It turns out that it's much easier to build the network than it is to fix it after a piece of it dies. So we would like all of that. We would like for it to scale, we'd like for it to be converged, so if something dies but it fixes itself, find paths that are both efficient and fair. And when I say fair, I use that term really loosely. We'll define that as something other than what you think it is. And but it has to always be correct and it has to be distributed. There's no internet super God machine that picks routes in the internet. So let's talk of something very simple. Just like we've been doing before, we're going to come up with something simple, find the flaws in it. We're going to like it because it's simple. We're going to find the flaws in it and fix it as we go. So like let's say we have a network. All right, we've seen network kind of like this before. All right, so before we've looked at this from a data link layer, right, where everything is equal. Of course, everything in the internet is not equal, right? We may have links that have different properties. And so, firstly, let's discuss what those properties might be. So, name some of the properties of a link in the internet. So data link network has all the same properties, right? Because it's engineered to be the same. So, but in internetworking, they can't possibly all have the same properties, right? Because packet sizes might be different. The maximum distances might be different. There might be all sorts of things that are going on in this network, right? So what are some of the things that we can differentiate network links for? Delay, which is latency, right? Which almost always is also distance, right? They're all interconnected to each other, particularly inside the core of the internet where most things are not going wireless, right? So distance is, unless you're jumping to a satellite or back down, then distance is 2/3 the speed of light times the distance, and that is your latency, right? Or your delay. Switching time is usually negligible. What else?
Whether B and C have a monetary relationship?
Oh yeah, the biggest one is monetary relationship. How much does it cost for me to use this network? And if you are working at ISP, when we calculate paths or distance in the network, which is really a number that we come up with an algorithm that adds all of these things that we're about to discuss together, right? Cost is heavily weighted, right? So money. So latency and money. What else? Huh? Bandwidth. Right? Can you have a high data link or a high bandwidth link that is longer than a short band or a short distance link? Right? Can latency and bandwidth, are they intertwined in any way? No, not really. Right? So you, like, let's say you had this crazy fiber bundle that went from hypothetically went from LA to Australia, right? It's a fiber bundle this big around, has 10 terabit link, right? Well, it can have 10 terabit link, but you could have a 56K modem that is communicating a shorter distance, right? And while you wouldn't be able to transfer as much information across that little tiny link, right, it would certainly arrive faster, right? At least the first packet. Right? So if you're sending tiny packets, then latency might be a bigger deal than bandwidth. And if you're designing a network for an automobile, you really start thinking that's important. Because if it takes a long time if you have to go to Australia and back, you probably have already hit the pedestrian in front of you if you're designing autonomous vehicles, right? So bandwidth and latency are not tied together at all. Latency is literally just the distance. And it's really 2/3 the speed of light if you're in physical medium, or is the speed of light if you're in air. That's it. What else? So we got money, we got bandwidth, we got distance. What else? Those are certainly the big three.
I guess the number of connections that it has.
Oh, yes. So let's say that we have that giant pipe to Australia, everybody's using it because it has all this crazy bandwidth, and it turns out that it's free, right? Eventually we might be able to fill that thing up.
Like the Ohio Turnpike.
Yes. It's like the Ohio Turnpike. Should have made it a toll road or whatever. Get some cars off of this road. This is crazy, right? So it might just get congested, right? Anything else? Those are definitely the big three, or big four. But for right now, let's focus on the things that are inherently present in the network all the time, things that are static. And the reason we're going to do this is because we're going to look at quality of service later for when the Ohio Turnpike gets congested, right? We'll also look at things like, hey, we know it's going to be congested at rush hour, right? So we might act as ways to find better paths around it. Right? And the internet is not, despite Ted the Tube Stevens coming up with the series of pipes, for the analogy of traffic flow actually is relevant to network flow, right? There are times of day when certain places are bad, right? And so those times of day right now are usually between 6 p.m. and 10 p.m. wherever you are. So if you're on the East Coast, right, their times of day happens 2 hours before ours and ends 2 hours. And that's the reason is streaming media. So while you be at work and you're listening to streaming music is nothing compared to streaming video when you go home and you hit Netflix, Hulu, whatever on demand, whatever you're going to do, right? Particularly as people start cutting cable and stuff that normally delivers that content. So think about like what cable does with stream media. It could actually use the exact same technology. It could even deliver packets, right? But because cable would be much like a multicast system, where Comcast is delivering all the packets to each of the individual nodes at the same time because this movie was scheduled at this time, it would consume far less bandwidth than it would be to have it on demand. Far less bandwidth, right? Because we could just send one packet out through the network, right? Have it duplicated at all the endpoints and arrive at people's houses on a scheduled time. But on demand makes that useless, right? So on demand is inherently unicast. And that means that when you start a movie, right, then those packets are being delivered to you. And if somebody started at the same movie 10 seconds later, it's already too late to do multicast. there might be some interesting research projects on how to buffer that, and right. But then we might just move the media closer. Right, so, and Netflix actually does this, right? They have data centers in different parts of the country to host media. A lot of those actually belong to Amazon, oddly enough. And so they host media just closer to you, right? So it has less bandwidth to go through, or consume less bandwidth and have lower latency, right? So we can get, when we start talking about content streaming and stuff like that, we'll talk about that. But for right now, let's ignore all of the traffic jams. And let's just say, hey, we woke up this morning and there is no cars on the street. And we get to do whatever we want, right? So that is shortest path routing, right? You wake up, it is just the infrastructure. You're going to ignore everything else. You're not going to use Google Maps, and you're not going to use Waze to find your way around. Right? You're going to use the good old Random McNally map. So, we, as internet service providers, get to pick what our shortest paths are. Now, we say shortest path, that doesn't mean distance. It means all of these things up together. We're just going to assign it a number. We usually assign it in this class, we'll assign it a whole number because it's easy to do the math, but we assign it a number, and we just call that distance. Well, that might actually be distance. It could also be cost, most certainly cost. It might also be bandwidth, but these are properties of the network. So, we're going to assign all these links a number. Wear sunglasses at night. Okay, so we've done our algorithm, we computed out what our costs are going to be in between these networks. And we're just going to call that distance. And while H and C may be on different sides of the globe, right? And B and E might be next door neighbors, right? They can have different distances, right? It's not totally related distance. So we're going to find a path from A to E. What's that path going to be?
ABE.
So A, B, E. So A, 4, right? A to B is 4. B to E is 10. And so that is 14. Is there a better path? Sure. Lots of better paths. Right? What else? What's the best path? So A, B, C, C, E, right? 7. That actually is the best path, right? So by inspection, remember we are never going to get this in an actual algorithm. By inspection, we can see that there's the best path of 7, and that is A to B to C to E. Actually, so it turns out there's some really interesting things about this. So there's a property called optimality, which means that if you find a shortest path, then all of the subpaths are also shortest paths. You can actually think, if you think about this, you can reason out that this inherently is true, right? If there was a better path from so A to C is a sub path of A to E, right? If there was a better path to get to C from there, then you would have took it anyway to get to E. Everybody grasp that? There can't possibly be a better path to A to C than through B, because we found the shortest path to E. So all paths, all subpaths of a shortest path are also themselves shortest paths. Well, if you think about that, that means all we need to do to route, right, is if we find the shortest paths in here, right, from A to E, then we can eliminate whole swaths of paths that we need to find out. And so we don't need to find all paths, right? We just need to we need to discover an algorithm that we'll talk about on Wednesday to find that's comprehensive, but doesn't have to find every path, because we inherently find other paths as we go along, right? So while if A was in charge, we might need to find a path to F and E and D, we might eliminate everything else if we did that. And H, because it's out here by itself. So that's also interesting for making routing discoverable, right? Is we can find one path and take off whole swaths of the tree. The other thing is for forwarding, once we discover those paths, for forwarding, you no longer need to know where you came from. So if A was sending a packet to E, right, B does not need to keep track that it came from A, from a routing sense. It would be in the packet, right? But, so from a routing sense, B does not need to know it came from A, nor when it does arrive from C, does it need to know it came from B. Because all these are already shortest paths, so the next hop would always be the same anyway. Because once the packet left A and arrived to B, the shortest path from B to E is still this path. It has to be, it's a subpath. And every time when we arrive to C, the shortest path is directly E, it has to be, it's a subpath. So we don't need to keep track of where anything came from. Well, if we don't need to keep track of where it came from, right, and we can just wipe out whole swaths of information at one time as we're discovering paths, now we have the basis to actually discover routes and forward them without ridiculously large tables. Remember, spanning tree, you had to know the path to everything. And so if you had a million things on your data link layer network with spanning tree, you had to know the path to all of them. And that had to actually be the whole entire path, right? Now we can discover routes based on simple information that we gather about the network, and we calculate through algorithm, whatever that happens to be, and we just assign it a number. Now we can find shortest paths. The only real question is there might be two shortest paths. Like the numbers might be equal. What do we do then? Flip a coin. We just flip a coin. And now we can forward information through a ridiculously complex network, right, with only tables from neighbors, or at least it's not tables. We'll discover stuff from neighbors, right, but with drastically reduced tables. So if you want to go to E, and remember, we wouldn't be doing this with E, right? It would actually be hierarchical IP addresses, because we already discussed this, right? If you wanted to get to 128.10.00/16, right? That's just one entry, and it goes that way. And we can wipe out the actual addressing for all the internet just with this. There is a problem with it, and the problem is convergence, right? What happens if a link dies?
It's got packets going off the
You'll have paths going off the cliff for sure, right? But it also takes a long time. So we're gonna propagate this information out quickly. It turns out it takes a long time to actually propagate it out, an error out, when one of the links dies. So we can actually, and then the question is, how do we tell that it died? Is it possible for a router to die, but its data link layer is still connected? And the answer is yes, right? You could simply think of this as your home computer, right? So if your computer is running, the data link layer is active, right? Because it's just the NIC card that does this, right? But what if you blue screen, right? There's no processing happening above that, but the link is still active, right? Your switch thinks it's still there, right? There's no difference in a router with that, right? So while we could use link state to get some information, right, it doesn't solve everything. So we'll have to figure out a way to converge for that. And we'll see why the algorithms fail-ish in that. You get these circular references. All right? So we've only done like stateful inspections, like we're the network gods again, and we're looking down on this network, right? And we can see all the links, and we can just visualize, hey, 7 is the shortest path. A, B, C, E is the shortest path to E from A. Couple other things that we've done is that we've assumed that the links are bidirectional. They're not always bidirectional. Take a look at your Comcast modem, it is definitely not bidirectional, right? And so we've made some other assumptions that it's bidirectional, but in a real network, you can just architect around things not being bidirectional. So, but for right now, everything in this class will just do bidirectional. That way it doesn't get too confusing. And then the other thing that we're going to talk extensively about on Wednesday is that B, when it's doing its routing table, does not get to see the entire network. It only gets to see its neighbors. Because of link, because it's actually linked to A at the data link layer, right? It knows A exists. It knows that G exists, F exists, E exists, and C exists. It has zero idea about D, zero idea about H. H is even worse off. It only knows that C exists. But we'll still be able to discover all the routes.